Today at solving absolute value equations. So before we get into solving the equations, I would like to remind you that absolute values can be defined by parts, which means they act differently in different parts of their domain. So the absolute value of x is defined as just x if x is already positive, so greater than or equal to 0, and the opposite of x if x is less than 0. So we're going to keep this in mind when we start solving equations, that essentially we can rewrite an absolute value equation as two or more non-absolute value equations by defining the different parts of the domain, which means that for each of these, we need to figure out what our boundary points are, what our critical values are. And there's a critical value associated with every absolute value, sometimes multiple ones. So critical value in this case, where we have the absolute value of x plus 3, happens where x plus 3 equals 0. The reason 0 is the critical value is because to one side of that it's negative, to the other side it's positive. So I need to figure out where is it 0 because that's where it crosses over between positive and negative. So the critical value here is when x equals negative 3. This then divides the domain of real numbers into two intervals, where x is less than negative 3 and where x is greater than or equal to negative 3. It doesn't really matter where I include the negative 3. I always include it with the greater than or equal to. You just have to include it in at least one of those intervals. And actually, I say at least one. Include it in one of the intervals. Do not include it in both. It's kind of an arbitrary choice, but this is the one I consistently go with. Now we decide, how is the absolute value of x plus 3 defined in each of those intervals? So if I start with a value of x that's less than negative 3, negative 7, for example, negative 7 plus 3 is a negative value, so I need its opposite in order to make it positive, so the opposite of x plus 3. Whereas if I have a number that's greater than or equal to negative 3 to start with, like 0, 0 plus 3 is positive, it's already positive, so the absolute value of x plus 3 is just x plus 3. These two definitions of the absolute value are going to define two different equations for me, each for a different range of values of x. So the first equation is where I have the opposite of x plus 3, minus 2 equals 3x. And this applies for values of x that are less than negative 3. The second equation applies for values of x that are greater than or equal to negative 3. And for this, I just have x plus 3 minus 2 equals 3x. Each of these is a linear equation that I now need to solve. So let's go back to equation 1. Minus x minus 3 minus 2 equals 3x. Minus 5 equals 4x. So negative 5 over 4 equals x. And in equation number 2, x plus 3 minus 2 equals 3x. 1 equals 2x. 1/2 equals x. So far, so good. Except not quite. It's a bit of a theme in this unit that we have to be careful that the answers we get actually are answers. So with radical equations, when we square both sides, we lost a little specificity with regards to the positive root or the negative root, so we had to check for extraneous values. With rational equations, when we multiply by the common denominator, we lose those non-permissible values, so we have to make sure that our solution is actually a permissible value. And here, because each of these equations is only applicable in a particular part of the domain, I have to make sure that my answer actually is in that part of the domain. So in the first case, negative 5 over 4 is not smaller than negative 3. So I actually have to reject that. It's an extraneous root. On a future example, we'll talk graphically about where that comes from, but for now, it's not in the domain. I reject it. 1/2, on the other hand, is greater than or equal to negative 3. So I don't have any problem there. So x equals 1/2 is the only solution to this equation. So that's the basic idea. We're going to look at some equations where we have slightly more complicated. So either in this case, we're going to have two absolute value expressions, or else one absolute value expression that's a little more complicated. But in all of these cases, we start the same way. We start by identifying our critical value or values. In this case, there are two of them, because I get a critical value for the x minus 3 expression, and I get a critical value for 4 minus x. So my two critical values are 3 and 4. So 4 minus x equals 0, And 3 and 4 will therefore divide my number line into 3 regions. So I've got 3 and I've got 4. So I've got values of x that are less than 3. I've got values of x that are greater than 3 but still less than 4. And I've got values of x that are greater than or equal to 4. So 3 intervals. And in each of these intervals, I decide what is happening with x minus 3 and what is happening with 4 minus x. One of the easiest ways to figure this out is to just pick a number in each interval. So x is less than 3, let's try 0. 0 minus 3 is a negative number, so the absolute value here has to be the opposite of x minus 3. But 4 minus 0 is a positive number, so the absolute value here is just 4 minus x. A number between 3 and 4, so 3.5. 3.5 minus 3 is positive, so the absolute value of x minus 3 is just x minus 3. 4 minus 3.5 is also positive, so the absolute value of 4 minus x is just 4 minus x. Values greater than 4, so 10. 10 minus 3 is positive, so that's just x minus 3. But 4 minus 10 is negative, so I now have the opposite of 4 minus x. These 3 intervals are therefore going to define 3 separate equations. So I'm going to write 3 equations. The first equation, well, absolute value of x minus 3, this is for values x less than 3. Absolute value of x minus 3 is the opposite of x minus 3, but the absolute value of 4 minus x is just 4 minus x. So this is the equation I end up with. Distribute that out, I get negative x plus 3 plus 4 minus x equals 7. Negative 2x plus 7 equals 7. So negative 2x equals 0, x equals 0. Check that against the domain. Well, 0 is less than 3, so that's fine. So x equals 0 is a solution. Looking at interval 2, in this interval they are both positive. So I just have, for values of x between 3 and 4, the equation is x minus 3 plus 4 minus x equals 7. Now what ends up happening is that x minus x drops out and I have no x's left in my equation. And when I simplify it, I get 1 equals 7. Well, that's nonsense. 1 isn't 7. So that means I have no solutions in this interval. Now, when you were solving linear equations, if you ended up with something like that as your answer, you would just say there are no solutions at all. But here we already know that there is one solution. It just means that there are no solutions between 3 and 4. And we'll look graphically in a moment at why that happens. And our third equation, in this interval, x minus 3 is positive, but x minus 4 minus x is negative. So we have x minus 3 minus 4 minus x equals 7, which when we distribute is x minus 3 minus 4 plus x equals 7. So 2x minus 7 is 7, 2x is 14, so x is 7. Check the domain. I didn't write the domain, but we can tell that it's x is greater than or equal to 4. 7 is greater than or equal to 4. So no problem here. So we found a solution in the first interval and in the third interval. So 2 solutions overall, even though there wasn't any in the second interval. But 0 and 7 are both solutions to this absolute value equation. If I want to consider graphically what's going on, so let's look at what I've graphed here in red is y equals the absolute value of x minus 3 plus the absolute value of 4 minus x. And in blue, we see y equals 7. We can see that those two things do intersect when x equals 0 and when x equals 7. So graphically, I could have found those exact same two answers. But what I can also see here is that my absolute value function has 3 distinct regions, that it's actually made up of 3 lines put together in different parts of its domain. There's a line that applies right up until x equals 3, because that was a critical value. That's where this function turns, it becomes something different. 4 was my other critical value, so that's the next turning point. And I can see that in that part of the domain, there is also one intersection. So that makes sense why I found the 0 in the first one and why I found the 7 in the second one. But it also helps me make sense of why I didn't find an answer in between them. Because in between them, I have a line that is parallel to y equals 7. And parallel lines never meet, so I did not find an intersection of those two. Let's look at an absolute value where we don't have a linear. It doesn't change our overall concepts. We are looking for critical values, and we do that by figuring out where is the expression inside the absolute value equal to 0. So in this case, that'll be where x squared equals 9, or where x equals positive or negative 3. So even though I only have one absolute value here, I do still have two critical values, which divides my number line into three regions. X is less than negative 3, x is greater than or equal to negative 3 but still less than positive 3, and x is greater than or equal to positive 3. So in each interval, I'm going to figure out what happens with the absolute value of x squared minus 9. Values less than negative 3, so negative 6, for example. Negative 6 squared is 36. 36 minus 9 is positive. That's all that really matters. So in this interval, the absolute value of x squared minus 9 is x squared minus 9. Values between minus 3 and 3 will give me a negative number, so the opposite of x squared minus 9. And values greater than 3 will give me a positive number again, so just x squared minus 9. So in this case, even though I have three intervals, I actually only need two equations, because both outside intervals, so x less than negative 3 and x greater than or equal to 3, can be represented with the same equation. And I need a second equation for that central interval. So the first equation is for values of x less than negative 3 or greater than or equal to 3. And that is simply the equation x squared minus 9 equals 16. Easy enough to solve. X squared equals 25, x equals positive or negative 5. This is great because each of these is in a part of that domain. Negative 5 is less than negative 3, so I can accept that one. And 5 is greater than or equal to 3, so I can accept that one. So two answers so far. Looking at the second part of the domain, I've got values of x between negative 3 and 3. Negative x squared minus 9, bracketed, equals 16, which means negative x squared plus 9 equals 16, which means negative x squared equals 7. X squared equals negative 7. Uh-oh. At this point, I know I can stop because I can't take the square root of a negative number and get real answers. So there's no solutions here in this domain. So we get just two solutions to this absolute value equation. X is equal to positive or negative 5. Again, we can look at a graph to help us make sense of why that is. So in red, I've got y equals the absolute value of x squared minus 9. We saw in our last unit why that is. It's basically just the parabola that's been folded up along the x-axis. And we've got y equals 16. We can see the part that is represented by the original parabola is the part that was already above the y-axis. That was equation 1, and I can see that that does produce two intersections at 5 and negative 5. And I can see the part that got folded up over the axis in between negative 3 and 3 doesn't intersect with y equals 16. So I know that I have no intersections in that interval. Moving on to one last example where a couple of interesting things are going to happen, and we'll be able to see graphically where extraneous roots come from. So we've seen in the last two examples graphically why we get intervals with no solution and what graphically that looks like. But here we'll see why we can actually get a solution that isn't really a solution. So our critical values here, well, the first absolute value expression x plus 2 is equal to 0 if x equals negative 2. And the second one, absolute value of x minus 7, is equal to 0 if x equals 7. So these are my two critical values, negative 2 and 7. Dividing the set of real numbers into three intervals, x is less than negative 2, x is greater than or equal to negative 2 but still less than 7, or x is greater than or equal to 7. And I'm going to consider each of these absolute values in each of those intervals. Values of x less than negative 2 actually make both of these negative, so the opposite of x plus 2 and the opposite of x minus 7. A value between negative 2 and 7, like 0, is going to be positive in the first case, so this is x plus 2, and negative in the second, so the opposite of x minus 7. And for values of x greater than or equal to 7, they're both positive, so just x plus 2 and x minus 7. All of these have some different combination, so each of them requires their own equation. So 3 different equations. First equation for values of x less than negative 2, we end up with the opposite of x plus 2 plus the opposite of x minus 7, or just minus x minus 7, equals 2x minus 5. This is minus x minus 2 minus x plus 7 equals 2x minus 5. Move all the x's over to the right. I'm going to end up with 4x. Move the numbers over to the left. I'm going to end up with 10. 10 divided by 4 is the same as 5 over 2. So I find an answer, but it is extraneous because 5 over 2 is not less than negative 2. So I reject that. And when we look at the graph after finishing the rest of this, we'll see where that extraneous value comes from, why that number shows up. The second interval, x plus 2 is positive, but x minus 7 is negative. So I get x plus 2 minus x minus 7 equals 2x minus 5. This is for values of x between negative 2 and 7. And that gives me x plus 2 minus x plus 7 equals 2x minus 5. I'm going to gather all the x's on the right. They do cancel out on the left, so I've got 9 plus 5, 14. 7 equals x. Oh, now here I've got a little bit of a quandary because I told you it was kind of arbitrary whether I included the 7 in this interval or the next. I got a solution that is a boundary value, and I didn't include that value in this boundary, but I could have. If you did, you would accept this answer. I didn't, so I'm going to reject it because 7 is not less than 7. However, don't worry. I told you it was arbitrary because it doesn't make a difference. When I go into the next interval, I will get that answer again. So whether I chose to include it here or in the next one isn't really going to make a difference, which we shall see when we now solve this equation for values of x greater than or equal to 7. In this region, they're both positive, so I just have x plus 2 plus x minus 7 equals 2x minus 5. But I don't just get a nice neat x equals 7. Sometimes that is what will happen. But this is a little more complicated than that because here when I simplify, I get 2x minus 5 equals 2x minus 5. Well, that's true. That's always true. And when you are solving linear equations, if you got an answer like that, you would just say, well, x can be any real number then. But I still have to respect the domain that I have. So x can be any number in this domain. It's always true for x is greater than or equal to 7. So if I hadn't included the 7 here, I would say it's always true for x is greater than 7, but then I would have to include the 7 because I found it in the second equation. So either way, I'm going to include the 7. This means that the solutions to this equation are all of the values from 7 to infinity, always. So we've actually got 2 things going on here that I'd like to have a look at graphically as to why they happen. Why is that extraneous root a thing? And what is going on here in section 3? So let's look at the graph. In red, you can see y equals the absolute value of x plus 2 plus the absolute value of x minus 7. And in blue, we've got y equals 2x minus 5, the left-hand side and right-hand side of this equation. What is maybe not so clear is that they are overlapping over here on the right-hand side. So that actually fully explains what happened in section 3. Section 3, when I wrote that equation, both of those functions are actually just the same function. So this intersection right here at the critical value at the turning point is where x equals 7. And for every value greater than or equal to 7, these 2 functions are actually the same function. So that's why all of them are intersections. All of them are solutions to this equation. In the central section between -2 and 7, I can just see that one intersection. In fact, if I kind of think of this as being an extended horizontal line, I can see that's going to be the only intersection with that blue line. And if I look at the far left section, so let's highlight that in blue. If I look at this far left section, why did I find an answer? Well, if I think about this as extending, then I can see that those two lines would, in theory, intersect, and they would intersect when x equals 5/2. But because that part that I've drawn as a dotted red line isn't actually part of my absolute value function, it's just part of the line that makes up a part of the absolute value function. But as soon as I get rid of the absolute value, the equation doesn't know that. So the equation tells me, yep, there's an intersection. It's up to me to know that that equation only counts for values of x that are less than -2. So that's why we get extraneous values. And to practice this, you can look at the exercises in lesson 7.3 of your pre-calculus 11 textbook.